Hi, welcome back to Chemistry 1001, Thermodynamics. We're going to look in detail at whether salt dissolves in water. Now, we know that salt dissolves in water. What we're going to do is try and work that out using our ideas of entropy. So here's the question. Does salt dissolve in water spontaneously at room temperature? Yes, it does. Some things do not. For example, olive oil doesn't spontaneously dissolve in water. So there are cases where this wouldn't happen. But this is salt. Let's look at salt. If you didn't know how to do this, if you didn't know the answer, how would you find it out? What's the entropy change? That's the right question to ask. If the entropy change was positive, then the process would happen. That's what it means. So all we need to do is calculate the entropy change. So here is how we calculate delta S, standard, at 1 bar pressure, 25 degrees for this reaction. NaCl solid goes to NaCl aqueous. So we go to our tables and we Google or do whatever we have to do, and we get this data at 298. S for NaCl standard is 72, and S for NaCl aqueous, NaCl solid is 72, NaCl aqueous is 115, both joules per Kelvin mole. So we can calculate delta S for the reaction. Delta S for the reaction at standard conditions is S for the products minus S for the reactants. So that's the subtraction of these two quantities, which gives us a positive number, 43.4 joules per Kelvin, which is bigger than 0. So that would indicate, it would seem, that salt dissolves in water. So it's spontaneous, right? No, it isn't. Why isn't it? Because we haven't considered the surroundings. Not at all. Wrong. What is the entropy change in the surroundings? It looks like we have to look up more information. To get the entropy change in the surroundings, we need the delta H for the system. We need to calculate the heat given to the surroundings and divide by the temperature. So let's look at the delta H at 298. We go to our tables, we Google, and we get these two numbers. Heat of formation for NaCl solid and NaCl aqueous, 411 and 407, more or less. Kilojoules per mole. Kilojoules per mole. It's usually the case with delta H. I keep saying that, don't I? Okay, so delta H, standard conditions, 1 bar. Delta H for products minus delta H reactants. That's minus 407.27 minus negative 411. Two minuses gives us a positive, gives us positive 3.85 kilojoules. So this is an endothermic process. It is. So let's have a look. It's an endothermic process, 3.85 kilojoules per mole. Therefore, delta H of the surroundings is negative delta H of the system. That means negative 3.85 kilojoules per mole are sucked out of the surroundings and pumped into the system. That's what an endothermic reaction is. So delta S of the surroundings is 3850 joules. I've now converted 3.85 kilojoules into joules by multiplying by 1000 and divided by 298. That gives me negative 12.9 joules per Kelvin. Now we have delta S for the surroundings. Let's now add those two quantities together. 43.4 for the entropy change from part 1 minus 12.9 for the surroundings, and we get 30.5. So delta S for the whole system and surroundings for the universe is positive. That's lucky. That means it's positive. That means salt dissolving in water is spontaneous. Apparently, salt dissolves is spontaneous. It happens. But actually, even this gets a bit more tricky, because you know if you put too much salt into the water, it eventually reaches equilibrium and stops dissolving. So this really only applies to the very first part of the dissolving process, not when you've heaped in a whole lot of salt and the system has reached equilibrium. Hope you've understood that. See you later.